So our next speaker, Andrew Appel1, is going to talk to us about assuring software protection in virtual machines. I'm sure we'll discuss the abuse of verification.
Right. So what do we want to do in Java or .NET or virtual machines? We want to run component software. We want to put together components that talk to each other through rich interfaces, rich APIs. And you know, when you put together components, you don't always write them all yourself. You sometimes get them from the net, or you buy them from untrusted vendors, like I won't name them. And so what you might do is you might say, okay, I have some core functionality that has access to my crown jewel data that I want to preserve the confidentiality and the integrity of. And I have other stuff that I want to run anyway, because it's apparently useful. You know, it prints my documents or whatever. But I don't necessarily give it access to all the data. And sometimes I want to cut and paste data into that application. But I'll do it through an interface, and so I'll have access control that decides what to cut and paste. And this access control here is just stuff you write in Java or C# or whatever. It's private implementations of publicly available methods. Right? This is standard abstract data type encapsulation stuff. There's no magic here. But what you want to avoid is that the untrusted stuff bypasses all your carefully written methods and just grabs the data or modifies the data itself. So what we want to do is guarantee that there's no bypassing the interface. And that's a protection mechanism. And so the classic protection mechanism is virtual memory. That you put one thing in one address space and another thing in another address space, and if the non-core functionality that you don't trust so much tries to access the data, it'll get a page full. And now if you want to build component software this way, you get COM, which nobody likes COM. That's why we're all here, right? It's really clumsy for reasons you all know, and I won't explain. So that's one disadvantage, is you can't have fine-grained interfaces with easy interaction. And it's slow. But, you know, virtual memory is well understood, and we pretty much can rely on it. So that's good. But then there's this Java crowd, which says, well, you know, you don't need to put different components in different address spaces. You can put them all in the same address space, and the type checking will guarantee that components don't bypass their interfaces. So type checking is used here. Language-based security is a fancy buzzword you could use for it, as a protection mechanism. Often, if you have a protection mechanism, you're protecting against somebody who is not trying to cooperate with you. That's why you need a protection mechanism. So the question is, so what are the advantages of Java? Let me just run through them for you. That you can have fine-grained interfaces that are efficient and convenient to cross, rather than slow and clumsy to cross. Great. Okay. And furthermore, the protection at these interfaces is specified in terms the application program can understand. That is, you put the word private or package scope, what word is that? Or public or whatever on each thing, and the programmer who's dealing with that interface thereby understands the rules which are concisely specified for policies of protection. That's great. Can we take this seriously, though? I mean, what would it take to really believe that the Java virtual machine or the .NET virtual machine is guaranteeing this protection against users who are not cooperating, people who are writing these untrusted components who may be malicious? So here's your virtual machine. You've got the untrusted application developer running an untrusted source to bytecode compiler. And then you've got your trusted bytecode verifier and JIT compiler. You've got your trusted library code. And if all of that works well, then the untrusted application can't disrespect its interfaces, because the bytecode verifier will catch attempts to do that. And I have lumped all of this VM stuff into the trusted computing base of the protection mechanism. So what's the trusted computing base of a protection mechanism? It's the part such that if there's a bug in there, it could lead to a security vulnerability. That it all has to work accurately, otherwise somebody can bypass protection. And this is a rather large trusted base because, well, you know, compilers are big, even JIT compilers are big. how many lines of code can you write and be pretty sure that it's completely free of bugs, right? And even if you write them and they're free of bugs, somebody's going to maintain them. And it's not you, it's that other guy that's going to maintain it. And they'll maintain it until it has bugs. And maybe a 10th of those bugs or a 50th of those bugs will be security relevant bugs. So what's a security relevant bug? Well, I'll come back to that. Okay, so what I'm going to talk about in this talk is, first of all, what do you have to do to security relevant things in your JIT compiler, securing the libraries, and then securing the idiot application programmer. Okay, so how is the attacker going to attack you through the JIT? Well, the attacker is going to find a bug in the JIT. This is not hard. The attacker has a copy of the JIT. It's in everybody's virtual machine. Okay, and it's also not hard because the JIT will have bugs, and there are lots of attackers out there looking for bugs. And now you write bytecode that's type safe, but that the JIT incorrectly compiles to machine code that casts an integer to a pointer. And there are any number of little type inconsistencies you might have in the machine code that can then be exploited to cast an integer to a pointer. For example, once you have a class that statically is thought to be, an object that's statically thought to be of this class, but dynamically turns out to be of that class, you can exploit that. And so, it's just once you have any inconsistency, you can leverage that to, basically dereference any address you want. Okay.
So is there a history of people actually finding such bugs?
Yeah, well, so when the first generation of Java-enabled browsers came out, Wallach, Dean, and Felton found that more or less there was one security-relevant bug for every 3,000 lines of code. Okay, now those were particularly bad. Some of those bugs were in the Java interpreter or the JIT or the checker. And so, yeah, there was a history, especially in the first generation or two. I would guess that today's virtual machines are better than that. And there might be a security-relevant bug only 1 out of every 30,000 lines of code or 1 out of every 100,000 lines of code. They might be 10 or 50 times better. But I'm getting...
There's a long-standing breach instead of type safety. It's still in all the ones that are shipping.
Yeah.
Interface types.
I mean, we
The
just
hackers
made
are
a...
checking on invoke interface.
Yeah, I mean, there's
You can't
bugs in
believe it.
reflection, there's bugs in, there's...
Now we're gonna have to kill everybody in the room.
I interpret Ben's question a little differently. Have there been actual exploits?
Well, no, because nobody does anything,
Or is it
nobody
too hard to
really
tell?
relies on Java's protection enough to make it worth exploiting, I think.
Not yet.
Right?
Actually-
Nobody really careful would run untrusted Java code in the same address space with important data. And the question is, can we make it reasonable to do that?
I think that's not true.
No, that's not true. Yeah.
Yeah, I end up running Java all the time in my browser.
Yeah, I was gonna say, right.
Oh, but it's just your browser.
Right,
You can trust
if
your
you're
browser.
on a
Next to
PC,
my bank.
If you're on a
Pay my
PC, you're
bills
running an
online.
admin, most
Right, and the
likely.
bank runs Java too.
Does the bank run untrusted apps in its Java?
The banks have got far more
probably
problem with
less, yeah.
internal
Yeah, no,
exploits
it's
than
really
the
true
server
that there
thing.
are banks running Java on servers, but I think they're running their own Java that they more or less have trusted the process.
They're running WebSphere.
No, but Andrew's question.
They're
is,
not
do they
surfing the
down-
net and running apps.
Do they download apps from the users into their Java runtime?
No, worse, they download them from their own developers.
Yeah.
That's a separate security issue.
I know, I'm just, this is a problem.
But Andrew,
Yeah.
you're simply saying that this hasn't caught on, but I read this slide and I say, if I were at Princeton, this is how I would attack the JIT. I'm not convinced that somebody else, won't get the same effect by, you know, sending a worm to developers and sending it through email and getting bad things in that way.
Yeah, well, let me come back to that, because I want to talk about more than just this particular attack. And there are other ways to approach it. This is, I think, you know, the one that interests me the most. Let me continue. But think about the big question of whether you could rely on the Java protection mechanism seriously enough for real life. So one solution to bugs in the compiler as vulnerabilities is to not have any bugs in the compiler. And so, you know, if you believed in program verification, you would write a correct compiler and then prove that the compiler is correct. That'd be fun. We know that that could never work. Who are these guys? 25 or more years ago, Demilla, Lipton, and Perlis wrote a paper that was very controversial at the time, but is now the conventional wisdom, which says formal program verification will never work.